Right, here are the solutions for this homework assignment, Chapter 6, 64, 66, 70, and 72. Number 64. We have a high-speed railway car goes around a flat horizontal circle of radius 470 meters at a constant speed. So we're talking about uniform circular motion here. The magnitudes of the horizontal and vertical components of the force of the car on a 51 kilogram passenger are 210 newtons and 500 newtons respectively. So the horizontal and vertical forces. So I'm gonna, if we're looking at the person, if they're going around the circle, the horizontal and vertical components of the force on the person from the car are 210 newtons and 500 newtons. So first thing maybe we should talk about is, how did I know that they were going like this? Well, I'm assuming that we're looking at the person's like going into the page around the circle like this way. And the forces on the person from the car, there's got to be the horizontal part is toward the center of the circle, and the vertical part is the normal force of the seat up on the person. So that's why I've drawn them that way. Now, we know that there is actually no motion in this direction, so this is a normal force. And of course there's a force of gravity on them, which is also 500 newtons. And you can check if you want. They told us that the person's 51 kilograms, so 51 times 9.8. That is just about 500, right? So that's where that's coming from. And they want to know, first in part A, what is the magnitude of the net force of all the forces on the passenger? Well, these are all the forces on the passenger. So these two are going to balance out in this direction. And then toward the center of the circle, we have the sum of all the forces is 210 newtons. And if you wanted to say the direction, it'd be toward the center of the turn. And B, what's the speed of the car? Well, let's see, we know that the unbalanced force toward the center of the circle is equal to 210 newtons, and that's got to be equal to mv squared over r. So that means the velocity of the car is equal to 210 times the radius of the circle divided by the mass of the person. Square root of all that. When B, square root of 210 times 470 divided by 51 gives us about 44 meters per second. I have my calculator in, I don't know why I have it in this mode, but I have it in scientific notation mode. So it's telling me, oops, it's giving me everything in scientific notation, whether I like it or not. So you can see that that is just 44, right? At least times 10 to the first. Number 66. So we have a situation here. We've got a block here and a block here and a frictionless massless pulley here. Mass of the first block, this is first block, this is 2 kilograms, and the block on the ramp has a mass of 3 kilograms. And see what it says here. initially held in place. Block 2 is on a frictionless surface. So this right here, if you wanted to get fancy, you could say this surface has a coefficient of friction of 0. It's frictionless. And the coefficient of friction between block 1 and the surface of kinetic friction is 0.25. Right? Kind of like a block covered in felt on a ramp or a lab table. And the ramp here, this angle is 30 degrees. So, the pulley has negligible mass. Once they are released, the blocks move. What's the tension in the string? Okay, so I'm going to treat this just like we've treated all our problems of this type. I'm going to make force diagrams for each block. So on this block we have a gravitational force of 2G, and it's on a flat surface. It's not moving in that direction, so the normal force would also be 2G. And there's friction here. Once they're released, we know that they're going to move. This one's going to move to the right. It's going to go down the ramp. Right? There's no other. It can't go up the ramp. There's no net force in that direction. So that means the frictional force is in this direction. I know that you could put a little K there if you want to. You know, it says the blocks move once they're released, so you could put a K there if you wanted to remind yourself that that is the kinetic frictional force. And then here be the force of tension. And I know that that's winning because the blocks are going to move when they're released. All right, this block here is on a 30-degree incline, so I'm going to draw the ramp, and there's a dotted line. I draw the gravitational force, 3G, and I'll break that up into its components. It's my 30-degree angle, so this would be 3G cosine 30, and this is 3G sine 30. The normal force is going to balance this component. We know that there's no motion in that direction, so that would also be equal to 3G cosine 30. We have the tension here, and since the pulley is frictionless and massless, that is the same tension as this. There's no other tension, so I'm not going to subscript that as T1 or anything, because there's only one tension here. Okay, so I've got all the forces drawn in. Now, the sum of all the forces acting on this block were a tie in this direction, so of T minus the force of kinetic friction. On this block here, sum of all forces, I have, they're going to move down the ramp this way, so that the gravitational, this part of the force of gravity is winning, minus tension. No friction here, right? You could redo this problem if you wanted to, adding a different coefficient of friction or the same coefficient here, and that would make it a little bit more difficult, but not too much. But as it is, we have been told that this part of the ramp is frictionless. Okay, so I'm going to try to fill in some of the information here. Net force, or the sum of all forces, is equal to mass times acceleration. So that's 2a. The mass of this block is 2. Tension minus the force of friction is equal to mu times the normal force. So mu is 0.25 times the normal force is 2G. And I can simplify that or not. I think I'll leave it for now. Sum of all forces on this one, the mass of this block is 3, so it'll be 3a. That's mass times acceleration. 3G sine 30. I'm going to go ahead and simplify this because I know that the sine of 30 is 1/2. So that's going to be 1.5G, right, minus the force of tension. as is always the case with these problems where you have a Newton's third law pair, like tension or an interaction force between two blocks, if I add these two equations together, those should cancel. And if you're thinking to yourself, but that's what I'm trying to solve for, well, we'll come back and we can solve for that once we find out what the acceleration is. So I'm going to go ahead and add these together. So 2a, 3a is 5a. Tensions cancel out, and I get 1.5 g minus, that would be a half a g. So 1.5 g minus half a g is just a g. So that means, looks like the acceleration of these blocks is 1/5 the acceleration of due to gravity. And then, if I wanted to find the tension, I could use either of these equations. I suppose I will use this one, which says, doing a little bit of algebra, just adding this to the other side, my tension is 2 times A plus half, quarter times 2, that's half, plus half a g. So that's 2/5 of a g plus half a g. So 2/5, that'd be 4/10 plus 5/10, that's 9/10 g. So it's about 0.89, I suppose, right? Let's check that. 9.8 times 0.9, about 8.82. Let's call that 8.8 newtons. That's the tension. And just checking my answers as I go. That agrees with the answer that the book gives. I'm going to turn this around here. You need to ignore this stuff, just in the interest of conserving paper. Let's see, next we have number 70. We have here a conical pendulum. I like this problem, just because conical pendulum sounds pretty cool. And it's you have the picture in the book, so I'm just going to draw a cross section of it. It's moving around in a circle like this. And I'm going to draw a force diagram of it when it's at this. So it's going around this, right? And let's see what they tell us about this. The cord sweeps out a cone as the bob rotates. The bob has a mass of 40 grams, 0.04 kilograms. And the string length, that would be this right here, is equal to 9/10 of a meter. And the mass is, the string's negligible. The bob follows a circular path of circumference equal to 0.94 meters, so we should be able to find the radius from that. And they want to know what's the tension in the string and what's the period of the motion. Alright, so first of all, let's find the radius. So circumference is equal to 2 pi r. So I'm going to take that radius, the circumference, 0.94, and divide it by 2 pi, making sure I put that in parentheses so my calculator knows I want to divide by both of those. So that's about 0.15, 15 centimeters. Okay. And let's see what else we can do here. If this right here is 0.15 meters, then I think that we could figure out what this angle theta is here, right? Theta would be equal to the sine inverse of 0.15 over 9. So sine inverse 0.15 over 0.9. I'm just going to check my mode here. I'm in degree mode, which is what I want. It gives me about, say, 9.6 degrees. Okay, so I think I have enough information now that I can make a force diagram of what the forces that are acting on the pendulum bob here. This, by the way, I think this is, compared to the last two problems, that first one, 64, is pretty easy. 66, you know, maybe 2 dots, but only because it's fairly involved. There's a lot of math going on there. I don't think it's a particularly hard problem. It doesn't like stretch anything that we know. You just have to be real careful. This one, I think, is a little bit more difficult. So, anyway, that said, forces on the pendulum bob. We have the force of gravity on the bob, which would be 0.04 g. And then there's the force of tension. And now, before I draw anything else in here, I just want to point out that there must be, if this thing's moving in a circle, there must be an unbalanced force toward the center of the circle, right? That is not negotiable. And can I point out to you here that none of that force toward the center of the circle can possibly come from the force of gravity. The force of gravity is straight down, and we're looking for unbalanced force toward the center. That's perpendicular to this, so there's no component of gravity in that direction. That means all of the unbalanced force toward the center must be coming from the force of tension. So I'm going to draw that in here. And if we realize that, we might realize that it's this force that needs to be broken up into its components, right, where that's a 15-degree angle here. This would be a 75-degree angle there. So these, the force of gravity and that component of the tension, must be canceling each other out, and this must be the unbalanced force toward the center. There's no other way that that can happen. We know that the up-down must be balanced, right, because it's not moving this way. It's only going in the circle. All right, so if that's true, then this component here must be equal to also to 0.04 g, right? Those have to cancel each other out. And then I think we can do a little trig here and say, well, if that's true, can I figure out what the force of tension is? I think that's the first part, right? Yeah. So let's see. I could, if I want to know what this is, the force of tension, I know that I'm going to use the 75-degree angle. Oops, where did I get that 15 degrees? Jeez. Is that from the last problem? Maybe? 15 degrees on my brain. So that's not 15, that's 9.6 degrees. Sorry about that. You were probably wondering what the heck was going on there. Just me making a mistake. So this angle here then would be 80.4 degrees, right? Those are complementary angles. All right, so that means that the sine of 80.4 degrees would have to be equal to opposite over hypotenuse. And solving that for t, that means the tension is equal to 0.04 g over the sine of 80.4 degrees. Let's jam that into the calculator. Uh-oh, my batteries are low. 0.04 times 9.8 over the sine of 80.4. And I already checked to see that I was in degree mode. So that's about 0.40 newtons. And let me just check that before I go any further and tell you any lies. That is correct according to the book. Happy days. And now they would like to know, that was part A. In part B, they'd like to know what's the period of motion. Well, I think if I can figure out how fast it's going around the circle, I know that the velocity or the speed of something moving in a circle is 2 pi r over the period. And I guess we have an unfortunate possible confusement here. This is tension, right? That's a force. And this here, this t is period, right? So not the same t. And I think this is what they want. So if I can find the velocity of this thing, I think that we're in business. So t would be equal to 2 pi r over the speed. All right. Now, let's see, can I find the speed? Well, I know that the centripetal force, the unbalanced force toward the center of the circle, is this right here. And I now know what that tension force is. So that would be 0.40 times, this would be the cosine component if I use the 80.4 degree angle. And cosine of 80.4 degrees. That would be the unbalanced centripetal force. That would be, oh, there it is, it's still there, times cosine of 80.4. And that's about 0.066 newtons. That's the centripetal force. And I know that centripetal force is equal to m v squared over r. And we found the radius back before, right? mv squared over r. So the speed of this thing is equal to the square root of 0.066 times 0.15 over 0.04. I think that looks good. I'm going to get that in the calculator. Got to be careful, right? You need to try to muster up some compassion for this conical pendulum, as you really do care about such things as this, don't you? So that looks like 0.50 meters per second. And then I know the period, going back to here, the period would be equal to 2 pi r. Radius is 0.15 meters over the velocity, 0.50 meters per second. And that finally is going to give us 2 pi times 0.15 divided by 0.5, which is 1.88 seconds, something like that. I'm going to say 1.9 seconds because I kept two significant figures most of the way through here. So I think I'll report the answer like that. And through the books, oh my goodness, they have exactly the same thing. How about that? So that's a problem, a good problem. You can make your way through that. I think you're in good shape. And remember, if you make a little mistake somewhere along the way, you could try to be more careful, but that's not I think our main concern is that you can draw the diagram and figure out what these concepts are that you need to use to apply to this. All right, no more room on there. Last one here, let's see, what was it, number 72. A box of canned goods slides down a ramp from street level into the basement of a grocery store with an acceleration of 0.75 meters per second directed down the ramp. All right, so an acceleration of 0.75 meters per second. The ramp makes an angle of 40 degrees with the horizontal. You want to know what's the coefficient of kinetic friction. So, 40-degree ramp. Here's the box sliding down here Don't know the mass of that. I guess that's not going to matter. Okay, so let's see what we can do. I think we can go straight to making a force diagram of this. Drawing the ramp there as dotted line. The force of gravity will just be mg because I don't know the mass of it. I'll break that into its components, perpendicular to and parallel to the ramp. If you make them like that, like I encourage you to do, then the normal force will cancel out that part. And that part, while we're at it, that would be mg cosine 40, and this would be mg sine 40. So the normal force would have to also balance this mg cosine 40. And this is a pattern, right? We've seen this many, many times. Now we know that there's also some friction here. And it's sliding down, so you could call that kinetic friction if you like. And that's it. Maybe just to say a quick word here about that one of the common misconceptions here in physics is that there must be some force directed down the ramp if this thing's going down the ramp. There is not an additional force here. Once you break gravity into components, you can see, oh, there is part of gravity is in the down the ramp direction. That's the down the ramp force. It's because part of gravity, one of the components of gravity, is down the ramp, not because there's some other mysterious force here. So try to avoid that pitfall. All right, so sum of all forces acting on this box of groceries is the gravitational force. I know it's accelerating this way, so this is the winning direction, mg sine 40 minus the force of kinetic friction. Right? And then I'm going to fill in what I can here. So this was the unbalanced force is equal to mass times acceleration. That's Newton's second law. And I know the acceleration. It's 0.75. It's equal to mg sine 40 minus the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And I know the normal force is mg cosine 40. So it looks like all of the terms in my equation have an m, so that can cancel out. And trying to solve for mu, so let me move that over here. Then on this side I would have g sine 40 minus 0.75. And then I'd have to divide. This would have come over here. Sorry, I'm doing a couple algebra steps, so you can go back through these carefully if you want. Depending on your comfort level doing this kind of algebra, you might try to do that directly. You might break that into 2 steps. That'd be fine. And then just to see, put a numerical value on that. That would be 9.8 sine 40 minus 0.75 all over 9.8 cosine 40. And that looks like about 0.74. That's a pretty high coefficient for kinetic friction. That makes me, well, I suppose this grocery store is set up so that the boxes don't slide too vigorously into the basement. You would want that. It might bruise your tomatoes or your bananas or your grapefruits. Well, I don't know if grapefruits bruise, but anyway, might damage groceries. So just check there. That is the correct answer. So there you go. Those are good problems. Don't forget, there's great value in redoing physics problems. I think that there's little value in looking at something like this. Let's see. Okay, so and then trying to convince yourself that you have studied. I don't think that that works very well. There might be a very small minority of people that works for. but I certainly wouldn't be one of them. I would need to go through and work this problem. So if you find yourself with this or any of the other problems in this video, you feel like you want to do these again, then do them again, right? You have the video to back you up. If you get stuck, get yourself to the point where you're unstuck and then continue to work on your own. But I suppose you know at this point that I'm a big fan of trying to get you to do it yourself. So it's there's enormous value in that. It's the only way really to make it happen, I think. So, nighty-night.